Okay. Okay, so welcome to everyone for the last session of the MEPHISTO seminar. Today it is my pleasure to introduce Eran Tal, Associate Professor at McGill University. Eran has shaped much of the contemporary philosophy of measurement, developing a distinctive model-based epistemology and more recently, a pragmatist approach to the factuality of measurement results. Today, he will offer us a new pragmatist solution to the riddle of factuality. So thank you very much, Eran, for being here, and the stage is yours.
Thank you very much, Danielle, and thank you all for joining today. I hope you can hear me okay. I apologize for not being able to be with you in person today, but I was very pleased to receive the invitation to speak with your group. The title of my talk is Measurement, Prediction, and Fact, and it's a work in progress that I'm currently preparing for publication. So any and all comments are extremely welcome. To start, there are two claims I want you to consider, two types of claims about the values of quantities. The top claim is an expression of a categorical expression of a claim, a factual claim about the temperature. The temperature of object O is T with some margin of uncertainty U. The bottom claim is different. If conditions C1 to Cn held, the temperature of object O would be T with some margin of uncertainty U. That's a hypothetical conditional claim about what the temperature of object O would be if the conditions held. Usually, we think that measurement outcomes, measurement results, the knowledge we get from measuring belongs to the first kind, or it should be expressed by claims of the first sort, categorical claims, claims about what the temperature is. After all, thermometers are supposed to tell us what the temperature is, not what the temperature would be under some conditions. And that's how we widely treat measurement outcomes. And this seems to be epistemically important, especially for the ability of measurement outcomes to serve as scientific evidence. The evidential power of measurement is supposedly predicated or conditioned on their ability to provide us knowledge of what quantity values are, or more generally, measurand values are, not just what they would be under some conditions or under some assumptions. But there's a tension between our intuitions about the knowledge measurement provides us and the practice of generating measurement outcomes, the practice of measuring. Measurement outcomes, we know, are inferred from theoretical and statistical models of measurement processes. And I'll talk more about what that looks like later in the talk. But what I'll try to show you today is that these models of measurement processes cannot be independently tested. They cannot be tested independently of some other model, of some other process. In other words, measurement outcomes turn out to be the consequences or predictions of theoretical and statistical models that are only compared to each other rather than compared to something independent of models, whether it be some independent observation or signal or cause. At least with the quantitative exactness that we expect from measurement, we simply do not get this sort of independent test. So it seems that if we simply if we simply look at the practice of measuring, measurement outcomes shouldn't be expressed as categorical claims about the temperature, what the temperature is, but rather as hypothetical knowledge claims about what the temperature would be if some model was adequate. And that's a problem, or at least it's a tension between our intuitions about what the knowledge measurement provides and the practice of generating and inferring measurement outcomes as we know it. I'm calling this tension or problem the riddle of factuality. And I'll spend today going through a few different ways of solving it. There are in the work I'm writing, there are 4 accounts: empiricist, information theoretic, causal, and pragmatist. Today, for lack of more time, I'm going to skip the information theoretic accounts and focus on first empiricist and causal accounts. I'll show that empiricist and causal accounts, as they are formulated currently, are inadequate solutions to this riddle. They do not provide us with an explanation for why we should think measurement provides factual knowledge. And I'll then turn to a pragmatist solution that I think solves the riddle. So that's the plan for today. Okay, so let's start by talking about measurement and empiricism. And a lot of it will be rather broad strokes. So I'm sure there are subtleties that will come out during the Q&A, and I'm very happy to delve deeper into these subtleties during the discussion. But in broad strokes, when we talk about measurement, all measurement procedures involve some kind of observation, at least at some point. If you're an empiricist, you're committed to more than just saying that measurement involves observation. If you're an empiricist about measurement, you would say that measurement is a type of observation, a rigorous type of observation. Think about what you do when you use a clock. You count the ticks of a pendulum clock, for example, or you observe the height of a mercury column, or the height of water in a measuring cup to measure volume. If you're an empiricist about measurement, you take measurement to simply be a more disciplined, rule-based type of observation. The empirical content of a measurement outcome is determined by the observations you make. And that proposes, or at least suggests, a very straightforward solution to the riddle of factuality. Because if, insofar as you assume that our sensory perception is veridical, or at least that there's an overall reliability to most of our sensory perceptions, then that reliability simply transfers over to measurement. So insofar as our senses provide factual knowledge, so does measurement. There are different types of empiricist views and different kind of iterations through the history of empiricism. In thinking about measurement, one way of cashing out the factual status of measurement outcomes is through semantic reduction. Famously, Rudolf Carnap in the 1930s proposed reduction sentences as ways of translating claims about temperature to claims about observable, the content of claims in observation language, such as claims about the height of the mercury column, or the number closest to the top of the water line in a measuring cup. Then there are other attempts, conventionalist empiricist accounts they agree that measurement does involve various conventions, including conventions about which intervals of a quantity count as equal or unequal to each other. But they still submit that these human choices about how to measure do not affect the empirical content of these measurement outcomes. So the empirical content of measurement outcomes, anything to do with our choices of units or congruence criteria, those all the human conventions do not affect the empirical content. The empirical content of measurement outcomes is comes completely from the observations, and the conventions merely regulate the way we express those results. Another more subtle type of empiricism is representationalism, and that's the view that numerical assignments preserve relations among qualitative observations. I should say that being committed to the representational theory of measurement as such doesn't make you an empiricist. It's a specific interpretation of the axioms of representational measurement theory that I call an evidential interpretation that makes you an empiricist. That is, if you think that that it is possible to detect quantitative structure simply from the data itself or through an abstraction from the data without using any theoretical assumptions, that would commit you to an empiricist view of the sort that I'm critiquing. And to see the problem with these views, we need to take a step back and distinguish between instrument indications and measurement outcomes. Instrument indications and measurement outcomes are very different kinds of claims. An instrument indication, here's an example. The ammeter needle is between the 1.0 and 1.1 marks on the dial. That's an indication of an ammeter. Or if you think of a questionnaire or a test, such as a reading comprehension test, response option 3 was selected by the student on item 1 of the reading comprehension test. That's an instrument indication. It's a property of the instrument in its final state after it interacted with the object, or in some cases, the person that we intended to measure. On the other hand, measurement outcomes are the knowledge claims that we want to infer from instrument indications. These are no longer claims about the instrument. They're claims about the quantity of the the quantity, or more generally measurement value that we attribute to the object or person we're measuring. For example, the current in the wire is 0.95 ampere with a 0.05 uncertainty. Notice that the number we assign to a quantity need not be the numeral that appears on the display of the instrument. That's because we may be correcting the instrument for various errors, including systematic errors, errors that do not average out to 0 in the long run. Same with the questionnaire or the reading test. The respondent's reading ability is in the 80th percentile. That's an example of a measurement outcome, in this case, a norm reference, measurement outcome, reference to the distribution of performance in some student population. And measurement outcomes are quite different from instrument indication, not only in their object, that is, they pertain not to the instrument, but to the object or person or event being measured. They're also different in that they require a specific scale, and they involve some evaluation of uncertainty, either implicitly or explicitly. So now that we know the difference between instrument indications and measurement outcomes, let's go back to empiricism. And specifically, let's ask ourselves, what's the relationship between instrument indications and measurement outcomes? Do instrument indications determine measurement outcomes? And the answer is no. the empirical content of measurement outcomes is underdetermined by instrument indications. So it's not just that we could transform the scales we use by using different units, for example. The very empirical content of measurement outcomes itself is also underdetermined by instrument indications. And to see that, we need to think about what happens when we infer a measurement outcome from some specific concrete apparatus. Imagine that you're Galileo and you're trying to measure the free fall acceleration, small g. You roll balls down inclined planes, and you measure the time it takes them to traverse various distances of the inclined planes. From that, you want to infer the free fall acceleration. But to do that, you first have to make several assumptions. You have to model your measurement apparatus in certain ways. You see above a diagram of the way we now do it. This is not the way Galileo did it. We assume some idealized scenario. We make some assumptions about forces, about friction, and we under the assumption of that model, we infer what free fall acceleration would be. Notice that nothing is actually free falling in our experiment, right? So what we're measuring is not the real system as such. We're attributing a value to a measurand, G, based on our model, and the observations we make constrain the predictions of this model rather than determine the value. The value is, in other words, determined jointly by our observations and the model. Can you still hear me okay?
Yes, absolutely.
Okay. So in other words, additional theoretical and statistical assumptions are required to construct the abstract and idealized model of the measurement process. I didn't mention statistical assumptions, but you can very well imagine that when we repeat the measurement procedure again and again, we get slightly different results, and so we have to make statistical assumption about the distribution of these indications over time. For example, we may assume that they're distributed normally. And if all that's right, then the factual status of observations by itself is insufficient to confer factuality on measurement outcome. Even if we accept that our senses provide us with factual knowledge, we're still relying on the adequacy of our modeling assumptions, the theoretical and statistical assumptions we interpret the indications with, and those are not tested by the measurement procedure. In fact, underdetermination is much more pervasive than just what I've said. And in my work over the years, I've shown that not only are measurement outcomes underdetermined by observation, but so are other claims that we also make about measurement. For example, coordination claims. Those are claims that say instrument X measures quantity Y. So for example, this instrument measures time, or this instrument measures temperature, and so on. Even these claims are underdetermined by observation. Quantity individuation claims. Those are claims that of the sort instrument X and instrument Y measure the same quantity. Those are also underdetermined by observation. Quantity detection claims, claims about the detection of quantitative structure in our data. Those are also underdetermined by observation. And even accuracy claims, claims about how accurate a measurement is, are underdetermined by observations. To give you a taste of some of this, I want to quickly zoom into quantity individuation claims. These are claims about two instruments measuring the same type of quantity. So here are two instruments. We assume that they're both clocks, and we try to compare their ticks to each other. So imagine that you're using clock, you're observing the ticks of clock 1, and you plot them over the time axis using clock 2 as your standard. And if you use clock 2 as your standard, you see that clock 1 has a decreasing frequency. It ticks slower and slower over time relative to clock 2. But of course, if you switch the procedure and use clock 1 as the standard and measure the ticks of clock 2, you'll see that clock 2 has a frequency that's steadily increasing. Now, the question is perhaps unusual, but nevertheless important. Why think that both of these instruments measure time? In other words, why think that both of these instruments measure the same quantity? At least from the point of view of representational theory of measurement, they shouldn't be measuring the same quantity because there is no permissible transformation between their indications. The data that we get doesn't have the same structure. That's because the intervals of the quantity that clock 2 measures are ordered differently from the intervals of the quantity that clock 2 measures. Notice that I'm not talking about time itself, but rather about time intervals, right? So the intervals of the quantity the first instrument, clock 1, measures are not ordered in the same way. It seems that strictly from the data itself, we shouldn't be compelled to think that these instruments even measure the same quantity at all. But of course, we do think that they're both clocks. Despite their frequency drifts, we apply corrections to those drifts, either by taking clock 1 or clock 2 as standard, or by taking some other third clock, or something like UTC, which is a complex weighted averaging of many clocks. We take those as standards and we correct all the other clocks to the standard. But that presupposes that all these instruments measure the same quantity. In other words, the data itself does not force us either to accept or reject the claim that instruments measure the same quantity. Our modeling assumptions are such that we assume that they measure the same quantity, and then we test whether the consequences of modeling them as measuring the same quantity mutually cohere. So I hope that's clear how models feature in claims about quantity individuation from this rather brief sketch. But let me move on to the second type of explanation, causal explanations of the factuality of measurement. You may think, well, when we measure, we're interacting with something, whether it's length or time or temperature or pressure. Measurement is a causal process, and that causal process in the end has some effect, and that effect is the instrument indication. So differences in the magnitude of the measurement cause differences in instrument indications. For example, differences in electric current cause differences in the displacement of the ammeter needle. So couldn't we simply say that measurement produces factual knowledge because it tracks these causes? Measurement involves reconstructing the cause from its effects. We observe some effects, and from these effects, under some assumptions, we infer the cause. And if that's the case, then measurement outcomes are factual insofar as they report the detection of a cause. They report the detection of the magnitude of the measurement that that was the cause of observed indications. And there are various types of causal accounts out there in the literature. A few books here by Trout, by Cartwright, by Borsboom that take different variants of this view. In this talk, I want to focus on one such account by Luca Mari, Mark Wilson, and Andrew Mall, that in their book Measurement Across the Sciences, that takes a very close look at how metrologists model their measuring instruments. Metrology is the science of measurement. Metrologists are the physicists and engineers who work at standardization bureaus, like the International Bureau of Weights and Measures near Paris, and who calibrate measuring instruments, maintain standards such as the standard kilogram and meter and second and so on. So if anything knows anything about measurement, it's these metrologists. We better look at how they infer measurement outcomes from instrument indications. And here's Mari et al.'s account of how they do it. They say that the measurand, the thing we're trying to measure, is what they call an effective property, a cause that interacts with our measuring instrument. That's in the diagram. That's listed as the arrow going into the measuring instrument that says property being measured. That's the cause that we're trying to detect. Measurement outcomes, according to this account, are inferred by modeling this causal process. But of course, there are other causes, intervening causes, that also influence the indications of the instrument. Some of these are influence properties. Think about the internal resistance of the ammeter itself, or background magnetic fields. They also affect the deflection of the ammeter needle. Some of these are affecting properties. These are properties that affect the property being measured itself before the measuring instrument even gets into the picture. And modeling the measurement process involves making various theoretical assumptions about the causal interactions between all these variables, and allows correcting these various sources of errors. What a measurement model provides is what's called a calibration function. That's a prediction about the relationship between the measurement outcome, the quantity we're trying to measure, that's listed here as O, and various variables. One is the instrument indication itself, or multiple instrument indications, a set of instrument indications, and all the other I's, I1, I2, I3, are these various influence and affecting properties. Notice, however, that the calibration function here inside the box, this F, is a prediction. It's a consequence of modeling the measurement process in a particular way. And there are different ways to model the measurement process under various assumptions. In order for causal accounts of factual status, of factuality, to get off the ground, we need to be able to arrive at a factual knowledge claim about the measurement outcome. Simply a hypothetical knowledge claim about what the outcome would be under the assumption of this or that model just wouldn't do. We want factual knowledge claims about what the temperature is. And that's where causal accounts fail. To see that, think of a simple measuring instrument like the one at the bottom of this slide, a caliper. A caliper is supposed to measure the length of some object. between its jaws. Metrologists calibrate this caliper by modeling its various influence and affecting properties, and making various causal assumptions about the relationship between variables affecting the caliper, such as temperature and various other variables, such as the roughness of the contact and the Abbey error, which is the wiggle of various parts of the caliper. Then they provide a prediction of what the length of the object between the caliper jaws would be under those assumptions. But to test those assumptions, they have to use some measurement standards, such as the gauge blocks that are just above the caliper in this image. These are a metallic object of known length. But hold on, how do we know what the length of those objects are? Turns out metrologists have to model the procedures by which they measure the lengths of these objects. This usually involves something called a coordinate measuring machine, and those machines also have to be calibrated through a model that predicts the dimensions of objects. And I think you're starting to get the picture. Eventually, we go all the way to our primary realizations of the meter. Those are today various interferometers based on agreed upon frequencies of lasers, such as this neon laser. But even then, the modeling doesn't end. There's no convention waiting at the end of all this inference that tells you what a meter or a millimeter or a micrometer is. There are just more and more models. In the end, these models are simply compared to each other. The consequences of modeling different interferometer length standards are simply compared to each other and shown to cohere within the expected uncertainties. So this entire chain of models, notice that that the theoretical complexity of these models only increases with each calibration. There's never a resting point at which we can say that we've detected the cause, we've detected some independent confirmation of what the measurement outcome is. All we get is more and more sophisticated and supposedly accurate model-based predictions, but no independent confirmation of these predictions. Simply more and more coherence tests for these various model-based predictions. And this is what I'm calling an inflation of auxiliaries, because with each step, more and more assumptions have to be made, and more sophisticated and strong assumptions about causal interactions and about simply properties, theoretical properties, states have to be made. To drive the point home even more concretely, consider the case of the Kibble balance. This is a design of a balance that's considered to be one of the most, if not the most, accurate balance we currently have. Here is one such balance at the National Research Council in Ottawa, in Canada, where metrologist Carlos Sanchez is using it to measure the Planck constant. The Planck constant today serves as the basis for defining the kilogram. But before 2019, it had to be measured extremely accurately so that its value could be set in a way that made the kilogram after the redefinition consistent with the value of the kilogram before the redefinition. Before 2019, the kilogram was defined directly by the mass of a specific object, the international prototype of the kilogram. But to bring you back to this Kibble balance, the idea behind the Kibble balance is that it uses rather sophisticated quantum mechanical principles to determine the Planck constant using using only the base units of the international system of units, the SI, or also known as the metric system. That is, it determines the Planck constant only by using the definitions of the meter, the second, and the kilogram. But to do this, to know how accurate this instrument is, you of course need to model it. Here's what's called an uncertainty budget that that metrologists construct in order to evaluate how much uncertainty is contributed to their measurement by various sources. So type A is a statistical type of uncertainty. Then there are various so-called systematic sources of uncertainty, such as voltage, resistance, mass, gravity, velocity, alignment, and so on. You may notice that the uncertainties are in parts per billion, so they're extremely small. But to get uncertainties so low, you have to be committed to a vast web of theoretical assumptions. Not only is each row in this table the result of very careful measurement and calculation, each row in this table is associated with its own sub-budget of uncertainties. For example, the gravity uncertainties involved in measuring with a Kibble balance have to take into account the effect of the Earth's tides, the effects of polar motion and atmospheric pressure. They even have to take into account the effects of the attraction between the mass and the balance itself. So, in other words, the more accurate your measurement is, the more theoretically and statistically complex your model is. More accuracy means more commitments, commitments to stronger assumptions and to more assumptions about how the instrument works. Calibration does not free the causal models from dependence on background assumptions. The opposite is true. Calibration deepens the dependence of causal models on background presuppositions. So again, there is no point in this entire inference where we independently detect some mass as the cause of our measurement outcome. So what do we make of all of this? Should we simply give up the idea that measurement produces factual knowledge and acquiesce to the view that measurement outcomes are consequences that are conditional on model-based assumptions, that all we do when we measure is compare the predictions of various models to each other? In some sense, the answer is yes. We should acquiesce to the idea that there's no external confirmation for measurement outcomes independently of models. But that doesn't mean we have to do without the idea that measurement produces factual knowledge. Rather, what we have to do is think differently about what factual knowledge is. And this is where pragmatism gets into the picture. According to the pragmatist solution that I'm offering, the factuality of measurement is not due to any special ability of measurement to detect and isolate empirical structures or signals or causes. Rather, the presentation of measurement outcomes as categorical factual statements is a pragmatic choice. And this choice is justified by the convenience of expressing knowledge claims in the most modular way that is fit for the purpose at hand. So the modularity of knowledge is the ability to take some claims and repurpose them, reuse them in different contexts, and analogously to the way we can use a Lego brick, detach it from one structure and attach it to another. So modularity, and specifically epistemic modularity, is the ability of knowledge claims to quote unquote travel autonomously between contexts. A closely related idea is the idea of ignorance affordance. Ignorance affordance is that the knowledge user needs to know little about the context of knowledge production. Think about two factories on one in Brazil and one in Japan. The factory in Japan produces nuts, and the one in Brazil produces bolts, or the other way around, because now I see the image is the other way around. What makes them so confident that that in the end of the day the bolt will fit into the nut? You may say, well, it's the network of metrological calibrations that trace uncertainties in dimensional measurement to primary standards. And that's exactly right. What this network affords is ignorance. That is a very specific type of ignorance. The knowledge users in each of these factories, they don't need to know about the specific assumptions under which the coordinate measuring machines or interferometers or whatever the other factory used to measure the diameter of their bolts or nuts. They don't need to know about the assumptions that went into these measurements. As long as the entire network is calibrated, they can simply transmit the dimensions of these objects and be assured that they fit within the uncertainties ascribed to these measurements. And the conceptual kind of flip involved in pragmatist thinking that I'm proposing is that measurement outcomes are not modular because they're factual. Rather, they're factual because they're modular. In other words, it's not because we have independent confirmation of the lengths of these or diameters of these objects that we're able to ignore the conditions of the productions of knowledge about them. Rather, it's because we managed to produce a coherent set of practices, coherent set of instruments, procedures, and theories and models that make our knowledge modular. It's because of all of that that we can treat the outcomes of our measurement as factual knowledge. So you may ask, well, under what conditions are measurement outcomes modular then? And the answer is that measurement outcomes are modular because they are coherent and secure. So coherence is a combination of nomic coherence, coherence among the laws or functional relations among variables presupposed by models, and predictive consistency, consistency among the consequences of these models, the predictions or retrodictions of these models. In other words, the reproducibility of results. But coherence by itself is not sufficient because we want we don't just want measurement outcomes that are context independent. We also want those measurement outcomes to be robust in case of various failures of our background assumptions. And to do that, we also need security. That's the robustness of knowledge claims across a range of epistemically possible scenarios. And here I'm relying heavily on the work of Kent Staley, who has written about this notion of security of evidence claims. Metrologists dedicate much of their time and effort to securing measurement outcomes. So not only are measurement outcomes coherent in the sense of being nomically coherent and predictively consistent, but also metrologists go to extreme lengths to secure the measurement uncertainties associated with different measurement outcomes, to trace them to common standards. They use key comparisons by comparing different measurement outcomes produced by different labs to each other. They revise uncertainties of incompatible outcomes. And very importantly, they avoid contested assumptions, theories that have not yet been proven to produce consistent knowledge, or where physicists do not know how to apply a theory well, or to produce consistent predictions from a theory. These theories would not be used when you model a measurement process in metrology. So only the most secure and tested methods are used to analyze data and to model measurement processes, and that allows measurement outcomes to be secure across, that is robust across various epistemically possible scenarios, various potential points of failure. If my account is correct, then we have good reasons to shift from a truth-oriented thinking about measurement outcomes to a pragmatist or use-oriented thinking about measurement outcomes, insofar as we put them in a factual mode, in a categorical mode. Under a truth-oriented thinking, factuality is reducible to truth. When we say that that the temperature of an object is such and such, we're simply claiming that it is true, that in some correspondence sense of truth, that the temperature of that object is such and such. Under a pragmatist way of thinking, factuality is relative to use, relative to my need to communicate the temperature of this object to others. My claim is modular enough for me to treat it as a fact. Under a truth-oriented thinking, measurement aims to discover facts, not to generate hypotheses. But under a pragmatist solution, measurement is a form of data-driven modeling. It generates model-based predictions, and there's no requirement for it to go beyond or kind of externally to any model. Under truth-oriented thinking, modular knowledge behaves at best as if it's factual, right? There's this as if clause. But under a pragmatist way of thinking, scientific facts just are the most modular knowledge claims available for a given purpose. There's nothing more that we can or should ask of measurement. And that, I believe, solves the riddle. Measurement outcomes are factual, after all, even though models underlying measurement cannot be independently tested, even though all of the knowledge that we get from measurement is conditional or on this or another model. Measurement outcomes are factual because of their modularity, because of their coherence and security. Measurement outcomes can be used as evidence to test hypotheses because measurement outcomes are usually more coherent and secure than the hypotheses they're used to test. So this way of thinking explains why, for example, we still have justification for using measurement outcomes to test the predictions of computer simulations or of various numerical or statistical models, such as machine learning, data-driven predictions. In the vast majority of cases, the models that underlie the measurement process and that underwrite the measurement outcome, those models are far more coherent and secure than the models that underlie the simulation or the numerical method or the data-driven machine learning prediction. In other words, the difference between those two types of predictions is not in kind, but rather in it's a quantitative difference in coherence and security. Measurement, finally, need not be evidentially superior to other forms of data-driven modeling, such as theoretical prediction and computer simulation. So this, an interesting consequence of the pragmatist view is that we could, at least in principle, generate theoretical predictions that are just as coherent and secure as measurement outcomes. And in that case, we could use theoretical predictions to test our measurements. There are cases where arguably this is already happening that I'm happy to discuss. But for now, I want to thank you for your time and attention. I very much look forward to the discussion. And here are a few references from this talk. Thank you very much.
Thank you, Eran, for this wonderful talk. Now, as usual, we will have a 5 minutes break, and then we will back here and find a way for him to see us. Yeah, we'll work on that. Yes. And yeah, back shortly.
Me? Okay. Yeah, that'll be.
Okay, we are back. So, time for questions, comments, observations. Excellent.
Hi, thank you very much for the talk. Really appreciate, very clear. I was thinking, why in your pragmatic approach you kept factuality? Because my impression is that you only need epistemic authority. You say they have epistemic authority because they are modular, blah blah blah. Why do you need factuality? Our microphone are off, maybe.
No, I can hear you. Yeah,
okay.
Thank you.
So why keep factuality in a pragmatist approach?
Yeah. So the short answer is that we don't really need factuality as such. If you're already willing to accept that the evidential power of measurement doesn't require factuality, that all that evidential power comes down to is something like the degree of confirmation or degree of confidence, a justified confidence in a claim, and that you're convinced by my account that we have a higher degree of justified confidence in measurement outcomes than we do, for example, in the consequences of most scientific computer simulations and the consequences of most numerical methods or data-driven machine learning predictions. If you accept that, then we don't need factuality to establish evidential power. There are two issues behind the appeal to factuality. One is simply recovering an intuition. Right? There is a broad intuition that perhaps you personally don't share, but I think many people do, that measurement does provide us with knowledge about what the temperature is, not just what the temperature would be. So one of the goals of the pragmatist solution is simply to recover that intuition, to explain why we're able to keep going, move around in the world as if measurement outcomes provide factual knowledge, and still succeed in our everyday dealings and not just our everyday dealings with measurement, but also scientific dealings. How can scientists get by with reporting measurement outcomes as factual claims? If you open a scientific journal, you'll see that measurement outcomes is usually reported as, the mass of this molecule is, not the mass of the molecule would be, blah, blah, under assumptions X, Y, Z, right? Measurement outcomes are reported as factual claims. So one function of the pragmatist account is simply to explain why we can get by and why scientists can manage successfully and safely to treat measurement outcomes as factual knowledge, despite all that we know about how they're produced. So that's one function. The other function of the pragmatist account is to recover the directionality of testing. We usually use measurement outcomes to test theoretical predictions. We don't usually use theoretical predictions to test measurement outcomes. I'm acknowledging the term usually here, because there are cases where we could be using theoretical predictions to test measurement outcomes justifiably, but usually it's the other way around. And the pragmatist account uses factuality in order to recover that idea that testing is directional, even though measurement outcomes are strictly speaking hypothetical claims. Is that clear?
Can I?
Yeah, absolutely.
Okay, thank you. It's very clear, but but I think it's dangerous. It's dangerous because, of course, the usually is important here. There's cases where I would trust more a simulation in certain case where it's very difficult to measure. And if we talk about authority or credence, we can compare. But if you talk about factuality, automatically, people would say anything factual is better than something non-factual. So it's why I in a pragmatic approach, I find the factuality problematic because you're losing this aspect that sometimes there will be more authority for a simulation in the case where data are difficult to get.
In those cases, I would say that the simulation provides factual knowledge, or that it provides knowledge that is at least as factual as the measurement. Factuality in the pragmatist account is not a binary variable. It's a continuous variable. It's a degree of coherence and security rather than a yes/no type property. I see the type of danger that you're alluding to, and I share the intuition that it would be in a way simpler if we simply just gave up factuality altogether. But I think it is important to explain why we're able to use measurement outcomes as if they are factual claims, and I think it's a advantage rather than limitation of the account if we can also explain why is it that we can use the results of some computer simulations as factual, right? Why we can treat the results of some computer simulations as factual, perhaps as more factual than the results of measurement outcomes. I think that's an advantage of the pragmatist account rather than a disadvantage of it.
Okay, thank you. Yeah, I've got so. Hello, but this is actually coming in from online, not from me, but I've got Julien Spical here who says is joining us live on YouTube from Edinburgh. So, hi, Julien. Julien says, many thanks, Eran, for your very interesting talk. I have two questions. We'll do them one at a time. First, how do these pragmatic choices of what counts as factual that you talk about today relate to the legislative activities and measurement that you talked about in your 2016 Making Time paper? Are you shifting from a more transcendental approach to a more pragmatic approach, or how do you see those relate?
Yeah, that's a great question. I'm still trying to figure that out myself. So, by the way, Julien is the person who actually invited me to give this talk. So, special thanks to Julien for.
He is there. He saw the talk. So.
Yeah, no, I know, but I'm responding directly to a question from him. So it's I want to acknowledge his efforts in making this happen. This is something I'm still figuring out. So I'm very glad to have the opportunity to kind of think out loud and see what the others think. But to give you some background, in my 2016 article Making Time, I talk about the legislative choices that metrologists make regarding which realizations, which concrete processes count as better or worse realizations of a given definition. And those choices are different than the choices of the definition itself. So it's long been noted that part of measuring involves a choice of what's called congruence criteria or uniformity criteria for which intervals of a quantity count as equal, such as choices about which processes have a uniform frequency, right? is the rotation of the Earth more uniform, or is the frequency associated with atomic transitions more uniform? Today we go with the latter. For many centuries we went with the former. That's a choice. But legislative choices have to do with which concrete clocks we use to approximate the definition with. Even if we define uniform frequency based on an atomic transition, we still have to ask ourselves which of these concrete objects, concrete clocks ticking away in various labs, are closest to realizing the definition. The definition itself is ideal. And there I argued that we have an additional choice to make. Metrologists have an additional choice to make, and I call that choice legislative. Now, the legislative choices are not completely conventional, in the sense that nature does push back. Different choices of concrete procedures, concrete instruments, would result in different different properties of our measure of time, for example, our measure of length or mass. Our measurements would be more or less stable and more or less accurate, or involve more or less uncertainty based on the choices we make. But there is also a pragmatic aspect to these choices, in that we may prefer some of them on the basis of convenience, on the basis of the utility, or even on the basis of political and social constraints. For example, the International Bureau of Weights and Measures tries to include clocks from many different countries. And that's partially because all these countries pay membership fees to the International Bureau of Weights and Measures. And so there's an economic reason to include all of them. So I see pragmatism as already built into the idea of these legislative choices. There are practical reasons to choose this or that clock, say, as a or practical reasons to distribute weights among clocks in a weighted average in the way that, say, the International Bureau of Weights and Measures does. But there's a second half to Julian's question, which has to do with the transcendental aspect, which I know is of interest to many other group members here. I haven't mentioned the transcendental inspirations for this work, partially because I'm not quite sure that that the word transcendental really fits into what I'm doing. But there is at least a loose inspiration in the way I use models and modeling in my work on measurement. I use generally the requirement to model your measurement process and the specification of a theoretical statistical model of a measurement process is a necessary condition for the possibility of arriving at a measurement outcome. So in the very broad sense of specifying necessary preconditions for the possibility of measurement, the specification of theoretical and statistical model is a kind of transcendental requirement. It's not a very strong transcendental requirement in that it's nothing like, Kantian categories. and I would say it's not even as strong as something like a relativized or constitutive a priori, as some philosophers argue for those in other contexts. But if we need to translate this into Kantian, I would say that the legislative choices that metrologists make are closer to regulative ideals. They regulate the distribution of errors among various clocks, say, or different thermometers or different balances, in a way that allows the entire networks of standards to maintain security and coherence, while also balancing that with a more straightforwardly practical, social, even economic interests. I don't think that really satisfies even the minimal criteria for a condition to be a transcendental condition. But I'm happy to open this discussion and hear from others, including Julien, about what is there something still transcendental about my model-based approach after all this? I'm curious to know what you think.
It's a good question. You want to respond to that, Alsa?
Yes. There is somebody who wants to comment this final observation.
Why don't we let people think about that now while I'll do Julien's second question and we can.
Oh, yeah. Okay.
Yeah. So Julien had one more. He says, yes, what do you make of Alistair Isaac's work on high precision measurement, particularly of constants? He claims that high precision measurement can escape a merely coherentist picture because precision, understood as reduction of random error, can be assessed statistically and independently of substantive physical theory. It reveals a, quote, theory-independent kernel in the result.
Yeah, I've had many constructive disagreements with Alistair over the years, and I continue to really enjoy our exchanges. I disagree with Alistair on this specific point, but I first want to highlight the great value of the work that Alistair is doing, because I think he's highlighting a very important counterintuition, a type of realism that is different from the kind of structural realism about entities structural realism that about relations that is meant to subvert realism about entities that we meet in the realism literature. Usually structural realism talks about the relations among, say, the ratios of different variables in a theoretical law, and shows us that these relations, for example, persevere and are approximated across theory change, or that these ratios are somehow invariant. But all this the kind of standard structural realism story appeals to theories, appeals to laws as they are formulated in theories. And what Alistair is doing is he's saying, put the theories aside for a moment. If we simply look at the measurements, right? And we ask ourselves, when we measure, say, the proton electron mass ratio, right? These numbers, over years and years of measuring them, converge to just a certain ratio, right? And yes, there are broad theoretical commitments involved. Alistair isn't denying that, but there's a convergence of these numbers that is independent of the specific commitments of very, very high level, sophisticated theories like the standard model of physics, right? So we have reasons to be realist, according to Alistair, about some of these constants, independently of more more advanced theoretical considerations. So first of all, I think this argument has a lot of force, but where I diverge from Alistair is really on the specific question of what this convergence on quantity ratios means, what it teaches us. How far does it establish, or put it differently, whether or not these convergences can serve as a foundations of knowledge from which all other measurement outcomes can somehow get their factuality, right? Whether, in other words, these stable fundamental constant measurements provide something like an independent calibration of all our measurements, independent of any model of any specific measuring instrument. This is where we disagree. All these measurements, including the proton-electron mass ratio and the fine structure constant, all of these measurements presuppose, first of all, certain conventions of uniformity or congruence, the ones that I mentioned in my response to Julian's first question. And those are necessary preconditions for these constants to even being constant, right? If we measured time or mass with different congruence criteria, some constants would just disappear from our laws. Those constants wouldn't be there, and that's simply because the mathematical shape of our laws would be different, such that the quantities in question would no longer have a constant ratio. In addition to those congruence or uniformity criteria, there are more idiosyncratic specific assumptions about the distribution of measurement errors, including systematic measurement errors across our different instruments. It's precisely because metrologists distribute measurement errors the way that they do across different instruments that we manage to get this convergence that Alistair takes to be a sign of some independent confirmation. To me, that's evidence that that metrologists make certain choices that allow simple, stable constants to emerge from their measurements. Right? But it's the models of the measuring instruments that are doing the heavy lifting and allowing us to discover stable relations. For Alistair, it's the opposite. It's the stable relations that provide evidence that that measurements are getting at something external, some stable properties in the world, and in a way, this is really a kind of a rehearsal of arguments for scientific realism versus arguments for a kind of cautious agnosticism about measurement values that is similar to other older debates around scientific realism that I'm sure you're familiar with. So that's a very long answer, but I hope it at least clarifies how much respect and admiration I have for Alistair's work, and at the same time where we disagree.
Thank you. Are there other questions? Yes, something.
Now that it's the question period, can you talk about the informational account?
Yeah, sure.
Time, just a little bit, the flavor.
Yeah. So an information theoretic account of measurement would say that measuring instruments transmit information in some way, right? And in a standard kind of Shannon-Weaver-based information theory, sometimes called syntactic information theory, we would model a measuring instrument like a communication channel, where we have some signal coming in from the side of the world, the signal being, say, the mass of the object, or the temperature of an object, and so on. That's on Alice's side, right? The A, Alice transmits, and then Bob is us on the other side of the instrument, registering its indication. And information transmission is successful to the extent that the instrument is sensitive. That is, differences in the indication, say if we're thinking of an ammeter, differences in the deflection of the ammeter needle track the signal that is the current, the electric current entering the ammeter. In some ways, this picture is helpful. There are, for example, it's useful to model certain aspects of measurement, such as the level of noise involved in measuring, right? Some sources of uncertainty in measurement behave like limitations in channel capacity, right? They behave like interference in signal transmission, and they can be modeled with the same equations. But the problems start when you try to use an information theoretic account of measurement to ground the factuality of measurement outcome, to ground the claim that measurement outcome is simply a kind of signal detection exercise. And when you try to do that, important disanalogies start to arise between the information theoretic story and the measurement story. One really big difference is that when we have communication, we have independent access to Alice's message, right? We can independently ask Alice, what was the message you tried to transmit to Bob, and then compare it to the message Bob received and see the differences, see the errors. We don't have that with measurement. We don't have any independent access to the current or temperature or the mass of the object we're trying to measure independently of some other measuring device, at least not with the quantitative exactness that we need in order to detect errors, right? We may have very crude sensory perceptions of which masses are, which objects are heavier or which objects are harder, but not with the exactness that we need in order to measure information transmission or information quality. That's one problem, but there are other problems, other disanalogy between the information theoretic story and the measurement story. Another disanalogy is that measurement doesn't involve transmission, but rather transduction. This is a point that Luca Mari makes in many of his works. What we're trying to do when we measure is not reconstruct the signal in the origin, but rather convert that signal, transduce it to some other property. Say we transduce temperature into the volume of mercury, or we transduce current into an angle, the angle of ammeter displacement. A third disanalogy, and this is where I think things get really difficult for the information theoretic story, is that many of the uncertainties involved in measurement just don't come from the procedure at all, right? They don't come from the interaction that supposedly transmits the information. If you go back, recall those many tables of uncertainties, the uncertainty budgets of the Kibble balance that I presented earlier today. These uncertainties, some of them have to do with physical interference, like magnetic fields interfering with the motion of the balance, or with the current running in the coil. But some of these uncertainties have to do with background assumptions, uncertainties about the evaluation of fundamental constants that are being used in the calculation of the measurement outcome, uncertainties that have to do with the calibration of various standards that were used in the calculation of the measurement outcome, uncertainties that have to do with various error corrections, corrections for, say, gravitational potential, the Earth's gravitational potential, or with other kind of statistical error, statistical modeling techniques, uncertainties involved in the statistical approximation of various parameters that are idealized and therefore require some inference. All these uncertainties cannot be modeled as sources of noise. They have to do with the inference from the observation of the measurement process to the value of the measurement. And here you don't really have a good information theoretic account, at least so far. We don't really have a good information theoretic account of how to think of those as uncertainties related to signal transmission.
Thank you.
Other questions? Hazel.
Yes, thank you very much for the talk. I wanted to come back to one of the first questions we started discussing. You mentioned that you have some cases when you sort of, instead of verifying or testing a theory or hypothesis against measurement, you do the vice versa. Can you talk more about this examples, please?
Yeah, good. So there are several. So there's an interesting, first of all, philosophical debate going on for at least a decade or more now about the epistemology of computer simulation and about whether some computer simulations can produce evidence or perhaps even be used as measuring instruments. My own former doctoral supervisor, Margie Morrison, argued that under some conditions, computer simulations can provide evidence that is on a par with measuring instruments. There's a very nice article by Wendy Parker on data assimilation that argues that the results of some computer simulations in climate modeling can be used as measurement outcomes, and in fact are used very much like measurement outcomes. So to perhaps to use, we can start with her example, Wendy Parker's example from the data assimilation paper. She describes computer simulation, computer simulations of past weather, and these computer simulations are used to infer, say, the temperature of the ocean in a place where there's no thermometer, and it does that by simulating the dynamics of the oceans, the air, the solar radiation, and so on, in conjunction with measurement data from other points in the ocean. This is extremely important because when you want to try to predict future weather or even future climate, you want to have a regular grid where there's a thermometer every, say, 3 kilometers, right? But in reality, we don't have a thermometer every 3 kilometers in the ocean. So these data simulation results are then being fed into forward-looking climate predictions and treated as if they are the initial conditions of the simulation. So they're treated as if they are measurements. Wendy Parker argues that there are good reasons to think of those as measurement, in as much as all measurement is model-based, and there is no the basic requirements for measurement, namely the ability to calibrate a measuring instrument against known quantity values and use the theoretical statistical models to extrapolate or interpolate from those values to unknown values. That basic requirement is met in the case of these computer simulations. I think that's an interesting argument, and I think that that it's a case where computer simulations, where there's a strong case to think of computer simulations as measuring instruments. Now, that doesn't completely answer your question yet, because the question is, what if we had a thermometer there that showed a different temperature than the computer simulation? Wouldn't we trust the thermometer more than we do the computer simulation? And in that point, I would agree that yes, we haven't flipped the directionality of confirmation in that case, because the background knowledge for thermometry is still more coherent and secure than the background knowledge involved in these computer simulations. Where things start to get more tricky is when you look at the way some measurement standards are themselves based on computer simulation. So if you look at thermometry again, but you go all the way up to the most accurate realizations of the Kelvin scale, especially to acoustic gas thermometers, a big part of the uncertainty budget of an acoustic gas thermometer, which serves as a standard for calibrating real thermometers, comes from a numerical simulation of the gas that calculates the speed of sound in the gas that is used for the standard. So already some of the uncertainties involved in calibrating a physical traditional thermometer to the Kelvin scale, that inference already goes through a computer simulation, which I think is very interesting. going on with a series of examples, there are cases in chemistry and computational chemistry where computational chemists are allowed are able to predict with very low uncertainties what the say the bond angles of a given molecule are, and some of these are based on uncertainties that are starting to look like they're smaller than the uncertainties involved in experimental methods. So I'm hearing some background. Is that a
that was
question?
noise, but can you please continue? That's with this example of chemists.
There's people outside. It's people outside.
Yeah. Okay. So the computational these computational chemistry simulations allow you are in fact tracked by NIST, by the International Standards of Science and Technology in the US. There's a whole database for computational chemistry that NIST maintains, and that gradually you see more and more of the uncertainties reported by these computations shrinking below the uncertainties associated with measurements. And it's no longer clear, at least, when the measurement and the theory sort of ab initio or semi-empirical calculation, when those differ, it's not immediately clear which one is at fault. So I think even though we don't yet have a computer simulation that is a clear that is clearly superior to the best measurement possible of a quantity in each and every case. We definitely have now numerical methods that are superior to many many kind of ordinary, not perhaps the best measurement instrument measuring results.
Other questions? So I will ask one. Yes, can you say something more about the concept of modularity you were talking about, I think in slide 20, and the idea of autonomy that is introduced in reference to modularity?
Oh, sorry, you're talking about, sorry, modularity?
Yes.
Yeah. So the modularity of measurement outcomes is something we take for granted in our both in everyday life and in science. You move into a new apartment, and you want to know whether the sofa from the IKEA catalog is going to fit in your room, and you measure the room, and then you compare it to the measurement of the length of the sofa in the IKEA catalog, and you take it for granted, right? We usually take it for granted that the comparison of these two numbers is gonna give us theoretical information about whether the sofa will fit, whether the sofa is going to be too large or or small enough to fit alongside the wall. And notice that what we do when we assume that is we assume that the procedure and the underlying assumptions of the procedure of measuring the length of my wall and the underlying assumptions that were involved in measuring the length of the sofa by whoever, someone in IKEA who designed it and constructed it, that those assumptions don't really matter for our communication. That we can simply ignore the question of, whether did they use a ruler? Did they use what kind of ruler did they use? Did they use a measuring tape, or perhaps did they use an interferometer? We don't care. Right? We simply don't care how the IKEA employee measured the length of the sofa. We simply compare the results. And this is a mundane example, but of course, industry and commerce relies on it all the time. We can have a car manufacturing factory in Belgium that gets its car doors from a factory in Japan, yet they fit with the rest of the car perfectly, for the very same reasons, that the measurements are deemed to travel between these contexts, allowing us to completely ignore how those measurements were produced. The important bit of information that we need is the uncertainty. We need to know what the uncertainty is of that measurement in order to know what wiggle room we have, how much we can expect comparisons between numbers to be informative, and at what point small differences in number are no longer a good basis for decision making. So that's what I mean by modularity. Epistemic modularity really is a kind of context insensitivity of knowledge. And notice that this is in tension with some with some accounts of the epistemology of data that say that data only travel because we have metadata, because we have information about the provenance of that data. And I'm referring especially to Sabina Leonelli. I don't really have a direct disagreement with that view, but rather I want to highlight the source of the difference. Sabina Leonelli's examples come from areas in the life sciences, such as genetics, where data isn't modular, where there is no way to completely decontextualize the data and simply remove it from one context. Say one genetics lab produces information about some genetic sequence and then just transfers it to another lab. What Leonelli shows is that the issue is much more complex, and in some cases it is. Especially if you want to reuse data in ways that were not intended in the way that it was originally produced, you cannot simply ignore the way the data was produced. It's definitely true in cases of measurement in areas like mental health, for example. Measuring the severity of depression in one context, and I've shown this in other work, doesn't allow you to make inferences about the severity of mental health using the same questionnaire in another context, using another population with a different type of community, a different type of, say, health service, and so on. So I'm not claiming that everything that goes by the name of measurement is in fact modular in the way I suggest, but rather I'm pointing to a very specific, very high standard of success that is a metrological standard of success. Metrological reproducibility is an extremely high standard. It's built with the level of rigor that supports ignorance affordance, that affords ignorance of the sort that allows you to fit the IKEA sofa into your room. And that is the high level of high level of rigor and the high level of context invariant reproducibility that I'm interested in for this talk. I'm not claiming that that everything that goes by the name measurement fulfills that standard. I hope that's a little helpful.
Yeah, absolutely. Thank you. Somebody else? No, so I also wanted to ask another question. We could distinguish different kinds of measurement in the sense that, for example, we may perform a measurement because we actually want to know the value of something, like in the case of Planck constant you were mentioning before. But we can also perform a measurement because we are directly testing a theory, like, I don't know, in the case of 1919 eclipse, when general relativity was tested by the deflection of the light of the star behind the sun. Or we may
taking a bad measurement on purpose.
What?
Are you taking a bad historical measurement on purpose?
No. That's an example.
Imagine it was a good one. Okay.
Yeah, otherwise we can have other kinds of measurements, like detection. For example, when we're searching for the Higgs boson at LHC. So do we need some kind of differentiation between all these cases for what concerns your perspectivist, pragmatist approach, or not?
I don't think so. No, I think in both of these cases, when we want to just know the number, we want to know the Planck constant, or even we want to know the length of the sofa, or when we want to test a theory, such as general relativity or the standard model, the epistemology of measurement is the same. In both cases, in all of these cases, we would be constructing a model, an idealized and abstract model of the measurement process from theoretical and statistical assumptions. Test that model during calibration, and then make a prediction, a calibration function about what the value of the quantity would be given an indication or a set of indications that are produced to the instrument, and then using that instrument to produce the indication and deriving the outcome. From the point of view of the inferential structure of measurement, it would be the same. The difference has to do with the reasons we're using it and some of the decisions we'll make. So, for example, the decision to accept or reject a theory would be would involve further considerations that usually go beyond the measurement itself. It would we would, for example, have to compare the predictions of the theory, and those predictions would also have some uncertainty associated with them. And we'd have to use certain statistical methods to see whether the predictions agree. But the lesson that okay, I want to distinguish two things. First of all, there are cases when we measure just for measurement's sake. Ian Hacking used to call it a measurement fetish. There's a fetish for numbers. I don't want to kind of exaggerate how much of measurement is driven by simply the need to get to the next decimal point, but certainly some of the drive to for increased accuracy is simply self-sustaining. We want to get to the next decimal point of the, say, the fine structure constant or other constants, simply because it's a technological challenge. We're trying to increase the scope and the accuracy of our theories in a way that is very much reminiscent of what Kuhn called normal science. But that is, of course, not the only reason why we want that next digit. We want that next decimal digit because we also, there's a chance that we'll discover a new physics at that decimal digit, that new effects that were masked by the low uncertainties of older measurements that will be revealed in the next digit. For example, when you go from microwave based atomic clock like cesium fountains to optical atomic clocks, your atomic clocks become very, very sensitive gravimeters. So a difference of a few centimeters in the height of your desk, right? The height of the desk that or the table that holds the clock is going to make a discernible difference in its frequency. That's how that's how accurate they are. They're extremely sensitive to the tiniest fluctuation of gravitational potential, and that means that with every push for accuracy, we have the opportunity to discover testable differences in the test and deviations from the testable consequences of some theory. So the two goals are connected: the goal of just wanting to know the number, and the goal of wanting to discover new physics or to reject potentially certain predictions of our models. Those are ultimately connected in terms of the goals of metrology. It's just that theory testing involves much more than simply measuring. It involves additional inferences that have to do with the derivation of predictions from theory and the comparisons of those predictions with the predictions of a model of the measurement process. In the end, we're just comparing predictions, though. That is a point I want you to take from this talk, that in the end, when we test the theory against measurement, we're simply comparing the predictions of the theory with the predictions of the model of the measuring instrument. And the reason we decide for or against the theory rather than for or against the measurement is that the measurement, the background knowledge informing the measurement is more coherent and secure.
Thank you. Okay, so I think that we can call it a day, and we can thank our speaker again.